Thanks for letting me speak here. This is, I should say the first thing, this is joint work with my student Ben Ward. And the plan of the talk is as follows. So part one is the most important thing. It's definition plus the theorems you expected. Part two are examples. Part three are universal. Operations. And part four, if I get to it, is homotopy theory. So for the first two parts, this came about thinking about. So what I was thinking about, so the input was Feynman transforms. So I was thinking about Feynman transforms. And BV equations. So there's a paper by myself, the same Ben Ward and Javier Zuniga about this setup, and we were thinking about what kind of operatic or more general setup is behind these things. So the input here, so this is not, so this did not exist in vacuum, so we looked deeply at the paper of Getzler and Kapranov on modular operads, and then also very much at the paper of Borisov-Manin, and you will see this coming up. And so we came up with something, and then we figured out that this has relations to stuff that has been done by Getzler and maybe Costello. And what's the one from here? Berger and Morlake. And actually, well, I mean, this is pre everything else by Marco. So it's sort of a synthesis of all of these things that goes into this definition, and you'll see in a second. So here's the main character. So let's start out with some data. So what I will be talking about. So part one is completely abstract, so you have to bear with me. I'm just going to give you a definition, and if you haven't seen it, it might just be, you would say, I don't care. And then I'll do just the standard examples and see that everything, so there's the yoga that everything becomes a Kahn extension. Everything does become a Kahn extension, and everything is just a Kohl limit. So it's really nice. So what's the data? We start out, we have one category, which is a groupoid.
Is it V or no?
It's V. It's V for vertices, but I mean, I have too many. The problem is it's V for vertices, but they will be graphs and they will have vertices. So it's a calligraphy V. Then there's a calligraphy F, which is a tensor, so F tensor. So this is symmetric monoidal. Then I will consider a functor from V to F, and any such factors through the following way, where V tensor is the free symmetric monoidal category. And now finally, this is just a symbol, iso F. This is equal to just F with its isomorphisms, F with isos only. So it's the groupoid underlying F. And now we can give the definition. So
V tensor is free symmetric monoidal category.
Yes, category.
Or symmetric monoidal groupoid. Or is it a groupoid automatically?
What?
Is it a free symmetric monoidal category and it is a groupoid automatically?
Yeah, it's a groupoid automatically, exactly. The isomorphisms of objects, it's actually really, really nice. The isomorphisms of objects are completely split. They're tensors of isomorphisms of the thing. So I need this. This is very important.
And the second map from P tensor to F is a monoidal functor, I imagine.
This is a monoidal functor. That's the definition of a free symmetric monoidal category that you know. So sorry, this is that's this monoidal, right? That's
so you use the universal.
This is the monoidal extension.
Okay.
Symmetric monoidal for that matter. Actually, this plays a role in one of the examples. You'll see this in a second. It is symmetric monoidal. All right. So now I can make the definition. Yes. So and I apologize. I mean, my Euler font is not as good. So this is Euler F. The problem is, this is Euler F, or Fraktur F is a triple, namely of V, F, I, which satisfies the following axioms, as above. Which satisfies one I tensor induces an equivalence of monoidal categories between B tensor and iso F. So this is where Marker comes in. So we found this, but this is basically exactly sometimes Marker calls this a hereditary condition. So any morphism splits in the following way. I have x going to y. Then by axiom 1, this guy is isomorphic to some tensor product over some I. And the usual notation I will use for vertices is little stars, because they're supposed to be vertices, and I'll put an index v there to just make them an object, actually. So it's star v, and v in some set. I might as well call it large v. Yes?
No, just a little slower.
Yes, okay. So I'm just giving axiom.
Okay, any morphism composed x and this to y
and now I'm saying this morphism is given already by 1.
Yes.
Let me finish the diagram and then say this, put the quantifiers. Then there is some isomorphism here and some decomposition. So let me finish this, v and v. And here it's the tensor product over v phi v. So what is it? What is this? So so these phi v's, these are in f x v star v star I of v. And so if so this is for any, this is phi. So and this is, what did I call that? Maybe we just call it psi. Psi x, psi prime. So for given phi prime, there exists phi and phi v. Such that this type, right? So what this means is, so basically any object in there is just a tensor of these simple objects v. And if I map into it, into something which is composed of a lot of objects, I can split up the morphism into individual objects. So if you want to doodle, it's like this. So if I have several objects here and several objects here, and I'm looking at a morphism, so this is a picture of x, this is a picture of y, what happens is that I can break this guy into pieces. Well, now I don't have enough pieces, so let's just make it 2, which map here. So this is maybe v1, v2, phi v1, phi v2, and this is the map here, the actual map here. So this is phi 1 tensor function. So that's this condition, and then I can fit it on the board. So the third condition, this is just a smallness condition. So
where is y, please?
it's for any in F.
This.
It's a condition on the category.
I thought it's V, so V is X to Y. Okay, now I understand.
Okay, other questions? Because I'm almost done, and then the rest is just the rest is example. So and that's what I'm trying to solve. That's it. It fits on half a board. So and for all star, so I star the comma category is essentially small. So you may or may not care about this condition. It's because I want to do Khan extensions, and then I have to take colimits over the comma categories, and I want them to be small colimits. Okay. So let me just do the standard theorems, and then you'll see all the examples. So this is why is this a nice setup? So you can have the following thing.
What's the definition of it?
That's the definition of the Feynman category.
Feynman category. Okay. Feynman category is a triple.
Is a triple, yes. I think this is the most convenient. I fooled around with it a little bit, but I think this is, of course you could say it's a functor, but that's always a strange definition. The category is a functor. All right, so what do we want to do with this? So let me just see, where am I? Okay, so then the first remark, maybe I put a remark. I don't want to do this. We can also do this the same. We can do this in the enriched setting. Say over some category E. And the usual candidates are ER, just either leading groups, or ER is vec K.
Excuse me, may I ask a very stupid question?
Yes?
If I take F, what is F, yeah. F to be just a tensor, V tensor that you wrote.
Yes?
And
It's a
it
Feynman
would be
category.
just a
Yes. That is a Feynman category. That works. V and V tensor is a pair that's a trivial Feynman category. That actually plays a role.
All maps are on this side, of this type.
All maps in V tensor are this type.
So
So if you have a trivial example, that's fine, that's good, yeah. So a stupid example, but it plays a role, is you can take V tensor, and inclusion. This is sort of a trivial example.
Other examples?
Yes. There's a whole page full of examples. But let me just see what we sort of want to look at representation of this. So what does this have to do with operads or anything? So let me make some other definitions. So let's fix another toric category. Fix C, another monodal category, symmetric monodal.
Isn't this first example a universal example?
This is the universal gadget which will contain.
Is the first example a universal example in the sense that
No, it's a trivial. It's like a point. It's like an initial thing or something. No, it's really trivial.
every such triple is given by a functor from V tensor to F?
No. This is actually, that's why I didn't want to say this example. This is an example, but it's really trivial. You're not going to see anything from this. If you can wait till the examples, you'll exactly understand what's going on.
But
So here's an example.
another question is,
Can I-
I choose F to be abelian?
F to be abelian. No, that's the wrong idea. You don't want to have F abelian. See, this is the point. So let me just make one more definition, and then maybe actually we know what I'm after. So fix C. So
Excuse me.
yes.
What is the definition of C, a new tensor, new upper tensor?
V upper tensor. It's a free symmetric monodal category on V.
Free symmetric monodal category
On V.
on V. V is a category.
It's a groupoid. No, it's not a category in groupoids. It's a groupoid.
It's a groupoid.
It's not a category in groupoids. It's a groupoid.
Groupoid.
Yes.
So this is homomorphism of groupoid.
Yes. Which one? V into V tensor is, yes.
F is a groupoid.
F is not a groupoid.
F is category.
Yes.
V is a groupoid.
Yes.
Groupoid is considered as a category.
Yes.
This is factor.
Yes.
New tensor is category of groupoid.
It's a category which is a groupoid.
Category
Which is
it's a group of
Just a purely cut.
And it's and the relation to F.
Category means only one object with.
No. Category means category. Groupoid means all morphisms are invertible. That's what groupoid means. All morphisms are invertible.
You take tensors of objects, you take the maps.
In the triangle, you could write ISO F.
Yeah, you could write ISO F.
Okay.
You know what? Yeah, it goes to ISO F, and that is an equivalence. Exactly. So F ops in C. This is defined to be monoidal functors. So after this definition, I'll tell you what you should think about from this F, from the underlying F to C, and F mods in C. That was just functors from V to C. And then in the example, so details later, but let me details later. Details in 2. There is a Feynman category F for operads, and F operads ops in C are operads. Operads and F mods in C are what is usually called S or S modules or sigma modules. And the examples I will give, it's not only true for operads, you can do it for operads, props, properads, modular operads, whatever, wheeled modular properads and other things, non-connected things or whatever. So this is a universal gadget. We're specifying a Feynman category. There's actually not even a word for it. It gives you one operatic type. Yes, one operatic type.
It's better to make up.
Okay. Yeah, but then I can't write on the other side. I'm not that tall. I'm not Danish.
Could you relax I to be full and faithful instead of an equivalence of categories for what you want to do?
No. No, I want it to be essentially subjective. It has to be essentially subjective. I just want that every object is decomposed completely as these stars. Actually, and then full and faithful. Sorry, which was no. It shouldn't be. No. You want it to be essentially subjective. That's important, and it shouldn't be fully faithful because you want some morphisms which aren't isomorphisms. It's exactly the opposite. You want every object to decompose, but you want. So what this says is this reduces the complexity of the morphisms you could have, right? Because I want to have all objects decomposed, so there are little dots down there. And then I'm saying all the morphisms are generated by just morphisms to one of those things. So as soon as I know, so maybe I should say that, so there's maybe a remark. So if I know F is a Feynman category, F is a Feynman category, then all morphisms are generated by morphisms from X to just a simple object. That's what the condition says. So and so if I want to construct something like this, I give the vertices, and then I take morphisms like this, and then I take tensors of those, and those should be my morphisms. They have to be work with the given isomorphisms I already have. Okay? Because I already fixed the isomorphisms on the objects. I'll do examples. You'll see this in a second how it works. Okay, so so what are the standard theorems? So the standard theorems are theorem 1 and theorem 2, I guess. Theorem A and theorem B. So theorem 1, so if C is co-complete and tensor preserves co-limits in each variable, then there's an adjunction, then there is a monoidal adjunction actually even of monoidal category of symmetric monoidal categories between these F. So let's see, F goes this way, F mods in C to F ops in C, G. And G is a forgetful functor, so G is forget. So if I have a functor, so one of these things was just was a monoidal functor from F to C, and this was just a functor from V to C, but I embedded V into here so I can just restrict the functor to the isomorphisms. So that's the forgetful map, and there's this thing. So this is the free, so we have free things. So we get free. So F is free, of course. F is free. And then theorem 2, so now I have a triple, a TV. Where are my notes? I never know if it's FG or GF. There we go, GF. Especially not if I'm on the board. So GF, a triple. So every adjunction like this. Maybe I'm too fast. So there's a forgetful functor. This has a left adjoint, which is in principle given by Kahn extensions. So what's the content of the theorem? I'm saying that that is a monoidal functor. You have to prove this. For that, you need exactly this condition. That will show you that it's a, you should know this. You shouldn't be frowning. So you need exactly this condition, and then you can prove that it's a monoidal functor, and then there's actually on these things there's another there's another tensor structure here where if O is such a functor, O is say from F to C, then you can do O tensor O prime on some object X. You define this to be O of X tensor O prime of X. So this makes these guys into symmetric monoidal categories. It's another structure, and these guys even respect that symmetric monoidal category structure. And then the other thing you want is some sort of theorem like this. So this is a triple, and then there is an equivalence of categories. Between algebras over T and these F ops. C algebras over T in C and F ops C. So that's the standard theorem. So I will do the example. So in principle, you can read here. This is a meta theorem which tells you the things for operads, props, and so on and so on and so on. So there are 15 theorems which always say something is the algebra over some triple, and it works out this way, and they're all of this type. And I can give these examples. Let me say one more thing, and then I can say how this is related to some other stuff, maybe. Because I see Ezra frowning, I can tell you in a second. So that's theorem 2. And then one more remark. So one more thing is morphisms of Feynman categories. So what should you do? So you have two things. You have an F and you have an F prime. No. Oh well, I should have F prime. And so what should be morphism? So a morphism is a pair of functors V F. So what can you do? You have V going to V prime. In obvious notation, you have this included into F. You have f, and this goes into f prime, and you have some I prime here, and this should too commute. So this functor should be isomorphic to this functor. And so then the theorem above there this is a special case, so this is where this trivial example comes in. So there's a more, it's on this, so the theorem, so if you have such a thing, then there's f upper star from f, and then finally I think I should get to examples. So this is the last thing, so from f prime ops in C to F. The problem is that everything is called F. There are only two letters in the alphabet, F and V. F from F prime mods to F ops, sorry, not mods, also for the mods. And this has a left adjoint, a left monoidal adjoint, F lower star, going the other way around. And so the example here is, actually this theorem is much stronger. And the example, so the theorem up here, you see that if you take this trivial example, we have a morphism of Feynman categories of this trivial guy into the Feynman category. And taking the push forward without morphism gives us the left Kahn extension, it gives us a free guy.
Theorem 2 and this last one to prove they make sense reading like this. I mean, the first one is operads is the category of algebras over the monad, okay, and this one, okay, you have the left Kahn extension construction gives you the left adjoint. So what is hard to prove there?
There's nothing hard to prove.
Okay.
I said the main point is that you make a definition where you can prove these theorems. As I said, the whole point is it's a definition. And the question is, why does this work? Why do you always have the same proof? It's the reasoning is there in all these situations you have this nice. I mean, Marco. As I said, there's not much new. Well, there is something new, but there's a synthesis of many things. So why, if you prove this just by hands on operads or something, you always use the hereditary condition. And I put this into the axioms. Then this other idea is, I mean, this is basically goes back to Getzler-Costello, that you shouldn't treat the trees or something like this as objects as you often do. You should treat them as morphisms. And if you treat them as morphisms, it's fine. You can write down a hereditary condition like this, and it works out nicely. Then there's a nice paper by Ezra about patterns, where you actually assume that this works. You don't put in the hereditary condition, but then you assume that this works. But here I say, well, for these guys, if I have this hereditary condition, I don't need to assume that it works. I can actually prove that it works.
Well, wait a minute. So you're saying the hereditary condition is stronger than the axioms for a pattern, or it's equivalent?
I don't know of the back thing. I'm saying it's stronger. I mean, it applies. I think it. Well, actually, I don't even know. I don't even know.
Is a Feynman category is a pattern?
Actually, there is. I tried to think about this last night because it's. I would guess so, but I have a problem because these patterns. So then I have to do something. So it doesn't quite work. I mean, because your pattern is a pre-sheaf, so it goes from C op to something.
A pattern is exactly the data of a category and a functor into a symmetrical node category.
Right. So for your pattern, you would have to take.
In practice, of course, the groupoid of the symmetrical nodal category happens to be the free category generated by that groupoid,
right. But the condition on the pattern is that you have that the functor
is
on
probably exactly equivalent to this, but written in terms of the day tensor product, right?
No, I don't think so.
It's not equivalent.
I don't think so.
Okay, so your theorem is that this. Oh, you don't even know if this implies being a pattern.
Yes.
I see.
Because you have to check it on pre-sheaves. That's the sentence
in
I'm
every
going to say.
example.
In every example, this is of this
It's
type.
a pattern.
Yeah, in every example, it's a pattern.
Yes.
And in every example, you get what you call a regular pattern. So this is a regular pattern.
Right, I'd forgotten that word. Okay.
Yeah, I need
that was the word I was
so.
looking for.
And what I'm saying is that there's a problem. You have to do some computation, and this is geared towards doing co-limits. But then you take the opposite category of the pre-sheaves. So you have to be a little bit careful, because I'm saying that I'm assuming something with the tensor product and co-limits, and that seems to be going to limits, and that's sort of not so true in sets maybe. I got confused yesterday evening, but it was late. So maybe you can prove that. I don't think it's. I think what I think is that it implies that it's a pattern.
It sounds like it. Yeah.
That's probably true, although I didn't prove it. Okay, so this is kind of nice, and now we can do many things, all just the same. So let's do some examples, and there are basically 3 types of examples, which I want to. Let's go to the 2 examples. And basically there are 3 types. One is operad type. 2 is algebra over an operad type. And 3 is twisted operad type. And so, as I said, the construction was I tried to understand what was going on here. So I'll talk about Getzler-Kaplan of hyperoperads here. Hyperoperads is basically equal to enriched. All right. And so let me write the classical examples. Examples are all based on trees. So this is one. Oh, I'm sorry, on graphs, not on trees. That's wrong. And maybe for the sake of avoiding arguments about what I'm going to say, is I'm going to use the Borisov-Manin category of graphs. So this is that I found that one to be particularly a brilliant invention. So because everything becomes true. You can just provable. I mean, things and I'll point out what's going on. So what is a graph? So a definition. So a graph. So this gamma is the following set. So this is Euler F gamma, V gamma, D I. So this is all. This goes. Actually, I don't know when this first appeared. Maybe. Yes.
Having these flags and so on.
Flags. Yeah. These are flags. These are vertices. V is a map which tells you at what vertex the flag is attached. And I is an involution.
In 2 dimensions, Grothendieck dimension. It's first flags of the cells.
Yeah, so this is, and then you have 2 terms, so E of gamma or E gamma. This is the orbits of I of order 2. And tails of gamma. So I found this in some paper of Manin and maybe, well, I forgot, maybe it was you. No, maybe. T gamma, so this is how I learned it in school. T gamma is the orbits of order 1. So that's already convenient. So an edge has 2 flags, that's what this is saying. But it's really convenient because you can actually write down things. You'll see this in a second. So now the new thing in Borisov-Manin was what is a morphism of graphs. So what's a morphism from gamma to gamma prime? So this is a triple phi on the vertices phi upper f and I phi, where phi lower v is a map from the vertices of gamma to the vertices of gamma prime.
If I'm all the man and graphizing as the edges and every edge has two
Flags.
If the edge is made up of two flags.
So
Yeah, flags,
yes.
two vertices. I is take this flag to that one. And then the orbit is the edge. But we allow tails, so if there's no other edge, it's just a tail. Then the orbit, then I of it is
fixed.
it's fixed.
Draw a picture.
Do you understand?
Yeah.
Yeah, but flags are hard to draw, and I don't want to draw arrows. But I. Let me not put arrows on the flag. I don't want to have arrows on the edges. Now the arrows, because the arrows play an important role. So if I put them here, then people will be confused. So, and this map goes the other way around. And then finally, the one that's so this is 1 and 2. The one that's a little strange is I. So this is this I5. This is an involution on the following set. So I can take. This guy is surjective. This guy is injective. And then I can look at the flags of gamma prime minus the image of the flags of gamma. And since this is injective, this might be non-empty. And I5 is a map here with I5 squared is id. So again, it's an involution. And no edges, no elements, no flags, elements of order 1. And after I finish this, let me just give one example, and then it's pretty clear what is going on. So, and then let me, the ghost graph. So this is another definition, gamma of phi, the ghost graph. So this is gamma of phi. This is the vertices of gamma, the flags of gamma, the boundary of gamma, but the involution of phi. Example. And this is again, this helped a lot in clearing up how to say things. So let's see, what kind of things do we want to do? So this allows you to do most of the things you want to do, or maybe all of the things you want to do. All of the things you want to do in this context. So what are things you might want to do? You might, this is my notation for corolla, right? I mean, corolla is a graph with only one vertex. Okay? So let's make it less complicated. Let's have one corolla like this and one corolla like this. And it doesn't matter how I drew them. It's just corollas. Now, I would want to have a morphism of graphs. So this is a graph. Nobody said up there that it's connected. Okay, so this is a graph. It's two disjoint things of corollas, and you can see how this might connect. So what I can do is I can make a graph out of this. So now what are the maps? Well, I have the vertex map is these two vertices map to these two vertices, its identity. These three flags map to these three flags, these three flags map to these three flags. The other way around. So these three flags map to these three flags, these three flags. No, these four flags to these four to these four. So nothing actually happened, except that. So this is a perfectly valid map. Nothing happens here. Okay. Now I do another map where something happens. Now I contract the edge. And now something happened. Maybe these two vertices map to here. And these three map to these three, and those three map to these three. So sorry, I was getting ahead of myself. But now I want to have the composition. So now this composition, what happened was that I put together these two flags, had an edge, and contracted it. So now if I go back, the map on vertices is clear. The map on flags is these go to these, and these go to these. But then these two flags are not hit, right? And those are exactly of the type up there, namely flags that just disappeared. And what this is saying is flags can actually not disappear. The only thing that can have happened to them is they have been connected to an edge and contracted. And the ghost tree, so this gamma, so if this is phi, then the ghost tree of phi, this is exactly the tree which indicates which edges have been contracted. Which ghost edges, which flags have been spliced together and then contracted. Okay? And now I can give you a board full of examples.
So can you say that this category of graphs differs like from the usual one that you allow also for grafting?
No grafting you have.
Yeah.
The only thing you don't have is like inclusion of graphs.
Yeah.
So the usual one you would do it differently. I mean, I shouldn't say that, but the usual one you would take two maps of flags and vertices, and they both go in the same direction, and that would be good for automorphisms and inclusion of subgraphs. So the thing you can't do here is inclusion of subgraphs. That doesn't really work. So this is sort of not operatic. What you can do is so this is of course encoding in operads saying that I can actually do operatic. I take OM, and then I have circle i's, and I go to LM plus n minus 1. That's exactly what's going on here. Really exactly. Okay? And this is kind of nice. So now comes the point. So and this is maybe the confusing part. So I can actually say this now. So the thing is that when you look at operads and think about composition along a graph, it's the composition along the ghost graph. Okay, that's the thing. That's how you sort of go up one level.
Don't you want to give another kind of example?
What?
With Prof or whatsoever to convince that this setting includes everything?
Yes, let me just write a lighter table.
He still hasn't given an example of his
No.
hidden category. It's just an operation.
Yes. So let's look at the following thing. So where's my table? This is notation, and now comes the table. Okay. So basically, what we look at is always the same. So you look at this. So we get this category graph. So we get category of graphs. So this is the Boris-Osmani category of graphs. So now we look at the following thing. So usually, the first example of a Feynman category, so this is a basic example. There's the following thing. So V are the corollas plus isomorphisms. Maybe I should write this out.
So by
P by
corolla, you mean
CRL?
simple finite set.
Sorry. Yeah, it's a finite set in a sense. Yeah. Corolla. Well, hold on. Let me define it correctly. Corollas and their isomorphisms. So corolla is a graph with no edges and one vertex. So in that sense it's a set because it's a set of its flags. D has to be mapped to this one vertex, and the involution I just said is trivial.
So this is natural numbers basically.
It depends. It can be sets or natural numbers. This is actually, that's why I want V to be. This is why I chose V. Right. This is why I chose V to be whatever you want.
Yeah.
So you could choose natural numbers for operads. Actually, it's not natural numbers. Is not quite right. It's natural numbers. Well, and then the set given by these natural
So you
numbers.
don't make a distinction between input and output.
It depends what you want to do. This is a basic example.
So in the basic example, you don't.
And the basic example I don't. In the basic example I don't. And F, this is what I call ag, usually. So these are aggregates of corollas. So these basically this means that there are no edge graphs. And I should have said this category of graphs, this has a monoidal structure, this given by disjoint union.
So leaves for you are not edges.
No. I call them tails and they're not edges.
So
That's the definition up there.
Sorry, F is the free symmetric category of corollas? F.
Of corollas, yeah.
Yeah.
Sorry, no.
In this case,
So aggregates, so as objects.
Ah, okay.
Sorry, it's a full, aggregates of corollas, and we take the full subcategory of these.
Subcategory in bodies of
In graph.
Okay.
So objects are these, and morphisms are all graph morphisms from aggregates to aggregates. And then the theorem or the proposition is that this thing V, so usually I call it whatever G, which is for graphs V, ag, and I is a Feynman category. And basically all examples, all classical examples, are indexed over this.
And
Which means,
ops in this case is what? G ops.
I'll give you in a second. So how is this basic? All classic examples are indexed over this. This means that that these Feynman categories F have a map to G.
What is aggregate?
And now I can give you all the examples. Sorry? What is
AGGECCTES?
Aggregates. It's
Aggregates.
You concatenate them.
It's a word. It's an old word used for set.
Put
It's an English word. It means it's something like a set. It's before people knew what sets were. They sometimes called them aggregates, and they don't want to call them sets because they're sets of sets. It's just juxtaposition. You put things together.
Could you call it collections?
You could call it collections, but I don't want to call it collections because then I have CRL and
Then you would have
COL. Crude called.
You can call aggregates.
Yeah, aggregates is a good word. Okay, guys, isn't it still the same now? What is it? What is corolla? A corolla is a tree with one vertex and no edges. So
Only leaves.
only leaves.
If I translate another language, is it true that this is the group of finite sets and bijections?
You can yes. If you identify flags with the set, right? So this is
In
usually.
this case,
usually I would write star S.
usual operads and things like that.
Right?
In this case, we obtain usual operads.
No. Now I can.
Waiting for it.
Now I can say yes. We're waiting, but I mean it's.
I think just say G ops is.
Yeah, exactly. So now we have some categories. So what I'm going to say is the first thing is we have the Feynman category G, and then I will tell you what the ops are. So sort of I will tell you what the what you have to add, what the ops are, and I will tell you what you have to add and how you have to restrict the ghost general file. There's one definition missing. So I have this ghost vertex V, so I need one more definition. And so I have this, this is a Feynman category, and after it's a Feynman category, wherever that proposition is, but then I know that phi is this joint union of phi V, and gamma V of phi is gamma of phi V. So now your wait is over, because it's just a very simple list. So these things are actually new. I would call them non-connected, unmarked. Maybe I should make this. Let me just make this bigger. NC unmarked modular opera. And this is if you add nothing and you do not restrict the morphisms at all.
So this is G of ops, right?
This is G ops.
This is G of ops.
G
What
ops.
does it mean, non-connected, unmarked modular operas? What
It's
is
definition.
unmarked? Okay. Wait.
It's a definition. A modular operad has a genus labeling.
Yeah.
and modular operad doesn't have a horizontal composition. So NC means you have a horizontal composition, and unmarked means you do not have a label. Okay? But let me go through the things. So if you do the following restriction, if you add the restriction that restrict gamma v, so if you just do the restriction on gamma v, that gamma v is a tree, or maybe I should do this, gamma v is connected, then the g ops, maybe I should just do it like this, then these are just non-marked, unmarked modular. If you add gamma v is a tree, then these are cyclic operads. If you add genus labeling, then and put no restriction, then you get NC modulars. So this is again new. If you add a genus labeling and restrict the gamma v to be connected, you get modular operads. And now let me continue the table here in the same fashion. So what you have to do is add restrict. So if you want to do operads, then you have to add direction to the graphs, and you have to restrict that gamma v is a tree.
This is gamma v.
See,
This
this
is
is
gamma v. What's gamma v?
all the gamma v's. So for any morphism phi, so it's always a subcategory of graphs.
Oh, okay. So you can say that gamma phi is a forest.
Gamma phi is a forest, yeah.
Each gamma phi is a forest.
Right, exactly. This tree, and then you can do props,
Oh, I see.
and you add direction, and you say you have no wheels. Well, then if you don't say you have no wheels, if you do props, wheeled props. So you see I can go on wheeled props, add direction, and you allow wheels. So I mean, this just goes on. So whatever you want to put here, it's just a restriction. You either put extra structure on the graphs, like direction.
So this means that you change your Feynman category.
I've changed my Feynman category.
Yes, and for that new Feynman category, we get this.
These things as operads.
And also,
Plus-
you have to change the group weight, the corollas,
Well,
because
well,
the corollas,
the corollas,
some
because-
of these things
It
have
has
Yeah,
to-
if it's directed-
This Feynman category incorporates some data which includes the group weight.
Yeah, but it's basically you take the graphs.
His definition
Right.
is just
Oh.
Yeah, and so because if you have direction, then the automorphisms of the directed corolla are only Sn-1 depending on how you count. So it works all natural. There's nothing on. You can get non-sigma. Then you do planar here. Sorry, there's no restriction. The restriction is that it's again a tree, but then you have to add planar structure, and you have to add direction. And but you can also do non-sigma cyclic. For instance, this is cyclic, which is just planar, and gamma v is a tree, and so on. So, but then there's some nicer things, which aren't maybe not. So I'll put up two more, which are not really. They're actually on the usual list, but not so much seen.
Sorry, I didn't understand the difference between what was it, NC modular operand and modular
Not NC modular operand has horizontal compositions like in a prop. You can have disconnected surfaces. Surface. So you remember I have this thing called so one morphism which I didn't write down. One graph morphism is this. You take S, you take T, and you map this to S disjoint union T. So that's a graph morphism, which is the avatar of horizontal composition.
I can't see the picture. S disjoint union T, but it looks like connected in your picture. So what happened?
Why don't you put them one next to another?
Nothing happened.
It looks like there's only one vertex in S union
Yeah.
T, but surely it has two vertices.
What? No, this has one vertex.
Well, what do you mean union then?
Disjoint union.
You
It's,
take the unit of
it's a
the
disjoint union. The
Then
set of
surely
flags.
there's
The
two
set of
vertices.
flags S is here.
flags. Take the unit of the flag.
It's just a disjoint union of the
You
flags.
weld them.
Disjoint union of the
Of
flags.
the flags, yeah.
So you're joining them at the two vertices. Okay.
Yeah.
So you have a new operation. Uh-huh.
Which
So
is-
it's a completely different operation from,
Yes,
yeah,
it's
from
completely
any
different.
that occurs in modular opera theory.
Yes, exactly. No, you don't have
so
this.
what, are there any examples of such?
Yes.
Okay.
So those are the guys which have BV equations. So I may or may not get to that, but so there's old work like Kimura, Sasha Voronov, and the newer one with House and such. When you take moduli spaces of not necessarily connected curves,
And?
graded by genus, by order characteristic. So Schwarz did this. It's this is one. Schwarz modular operads.
And then?
And then?
But those
Nothing
are
in
they're just freely generated. But I mean, they're
No, they're
just
not freely
generated
generated.
by some kind of extension from a modular opera. They're not intrinsically different.
No, but the same thing for profs. Many profs are just kind of extensions.
In
from-
this
Well,
case-
right, that's what I mean. Is there an
in this case,
intrinsic,
yes,
is there an
but maybe-
example that...
Is there an
Other
example?
results.
With, I don't know. It's the same thing with the
Not
prop.
really a modular
I also have to admit that I don't know a prop which is not
All
just
right,
an
so there's,
extension.
the theory is isomorphic to the theory of modular operas.
No, props. It's the same thing. Like modular operads are to these guys as operads are to props. Proprads are to props. Thank you. Exactly. Proprads are to props as these guys, as modular operads are to these guys. But we can discuss later. Otherwise, I want to finish. So two more examples. So you can do operads with a multiplication.
I mean, that's just false. Props have directions on the edges.
Yeah, and these are those don't.
And
So
these
if you,
don't. So they've got nothing to do with props. So I don't understand.
actually, they do have something to do with props because there is a morphism that can take a con extension. But the whole point is, what I'm saying is, you know, propriads and props are both directed,
Yes.
and they're not the same. No. Now I take the graphs and strike L reference to direction.
Yeah.
On one side, I get modular operads, and on the other side, I get these NC modular.
I think there are isomorphic theories, actually.
No.
You can
No,
have
no.
relations on the disconnected parts.
Anyway, but so operads with a multiplication. So what do you have to add?
Oh, okay. But he has no example.
No.
Okay.
Okay, it's a question. But so far.
So far, exactly. They might have come up. So for what do you have to add here?
Yeah, of course.
You have to add a morphism. So this is kind of fun. You have to add a morphism from the antigraph.
Props don't exist.
So if you add a morphism from the antigraph to the corolla marked by 0 and 1, 2, this is what you have to add. And this is legal in the Feynman category. Because this thing, the empty graph is the unit for the monoidal category, which is generated by the empty collection of corollas. And if you check the axioms, it actually works out that you can freely adjoin these guys. So you can adjoin these guys to your category, and you get category of operads with a multiplication. You can also do A infinity multiplication. Well, then you need several morphisms going to n of these. And you can add them, and you get a category. That, again, can be represented as a category of graphs. That's kind of nice. So basically, these are trees. So basically, what you get are black and white trees here, and here, black and white trees. And here you get sort of these you get the conservative Solomon trees. So this is black and white trees like they appear in paper with Rachel Schwell, where we looked at the A-infinity bilinear conjecture. All right, so these are these examples. So maybe I should go quicker because I'm really running out of time. So example 2 was operad type example. So what we can also do is we start with an operad. Start with O, operad. And we take V to be just one object. Then V tensor, this has object 1 tensor n. But now this is the free symmetric monoidal category, so this has an action. So now what I can define, I define FO of 1 tensor n, comma 1 to be just O of n. And I claim this is a Feynman category. I generate morphisms with this, take this trinomial of tensors. I have Sn action on the left because I have to compose. That's why I said you have to be careful that you can compose with isomorphism, and you get this. And then what are the FO ops? In C, these are just algebras. Over C, over. And so you see now you have free algebras, no problem. You have the theorems 1, 2, and 3 always apply. And so you can also have nice, so what is something else which is kind of nice, maybe I should have said that, but this basically also goes, so let me put this as 1 prime. So what is the prop generated by an operad? Well, I have a morphism of Feynman categories by inclusion, the one for operads into the Feynman category, maybe just call this O. So this is whatever. O. So this is the Feynman category for operads. Well, maybe I should still keep the F. F operads. I should have practiced my Fraktur. So on the paper they all have Fraktur names. But anyway, so it's easier. And to F props, just by inclusion, Corolla is like this. Inclusion and I star is restriction. I lower star is the operad, the prop generated by the operad. And there was also an I lower shriek, so if it exists, this is the extension by 0. So in many of these things like modular envelope or if you have a modular, so there's always this question, how do you get a prop from a modular operad? You forget the genus labeling, you get something like this and you pull it back to props and then you get a prop from. So it's really nice. So it's just extensions. And type 3 examples, so I want to do very quickly, so these enriched examples. But what do these enriched examples look like? So what am I trying to do? I'm trying to do the following thing. So all morphisms are basic, but I have to tell you how to compose morphisms. Here actually I didn't, but you can guess that it's operatic. I'm out of time, so this is just operatic. So circ becomes, so circ in FO is gamma for the operad. And then this gives a nice composition of morphisms because this is associative. So what do you do here? So let me write this like this. So this is a composition of a morphism with another morphism. This one splits as these guys. The composition is this morphism. Then I can look at the ghost graphs. So this doesn't have to actually happen. But let me put it this way before even looking at the ghost graph. So I want to enrich. So I need a map from D disjoint union phi cross tensor with D phi 0 to D phi 1. And so this is, of course, the same thing as the direct tensor product of the V D phi V tensor D phi 0 to D phi 1. And this has to satisfy associativity. So if we go to the ghost graph picture, we get the following picture, which we find in Kapranov-Getzler for twisted operads. So here we have the ghost graph 0, here we have the ghost graph 1, and here we have these ghost graphs gamma V. And I would need a morphism from this tensor product into this guy to this guy.
What is D once again?
D is the enrichment. D of...
suppose D is a monoidal category in which something is enriched.
No, D is the functor which takes Hom sets, so D takes the Hom set of xy to the enrichment category.
So what's enriched about?
This is... so I'm trying to... okay, yeah, if you have an enriched category...
So what's an enriched category?
It's something...
category enriched in a monoidal category.
Yes.
Which every Hom is an object of some monoidal category.
Exactly.
And this monoidal category is D.
That's right.
Okay. So what is now enriched in D?
What is enriched in D is the Feynman category.
Okay, suppose we have a Feynman category.
What does that mean?
Which category?
I mean, there's V, there's F, there's V tilde tensor. There's
Yeah, it's E.
E.
E. It's enriched over something else. It's
But
not
what
enriched
is
over...
V,
F is enriched...
F.
Oh, sorry. F
Just say
F
enriched...
is a enriched symmetric monodal category.
Yeah,
Okay.
exactly. Over... Maybe I should have called it B here.
And V is what?
Enriched?
There's a bit of a problem. Well, there's no
You
group weight.
just say it straight in a
Maybe I should have... sorry.
Group weights.
let me. So the nice thing I should have said is that then I have Hom x y. So this tensored in D. So this is an object of D. Tensored Hom y star. This is an object in D. To Hom x star. And what I'm saying is that if I have elements like this, which give me a which is, so this is notation for an element in here. Maybe it's not standard, but this is actually your notation. So to each graph, the graphs give me the morphisms. To each graph, I can associate something, which makes it being an element in here. So if I have an enriched category, every phi is, so I have actually a functor from objects, from elements of phi into some monoidal category, right? It's the image in there. Yes? And your thing was that D of phi is something like the D of gamma is the determinant of the edges of gamma. That is what you should think. So it's some vector space which you associate to these morphisms, and then you have to have a composition, and then what you call a hyperoperad is just that these compositions define associativity. All right, this is the third type of example, and so let me briefly say two or three more things. Well, I did have a lot of questions. So there are fun things what you can do. So let me say what you can do, and then I'll do whatever. So let me write down the list and some statements, and then I can provide details for these statements. So one thing is, other things. So one, we can define a Feynman transform for special types of F. And what you need is that there is a grading on morphisms such that this F is basically free. F has homogeneous relations. Maybe I should say the examples are then again operads. You can actually all the examples above. All examples above. From what?
I have a question.
Yes?
What does it mean, Feynman transform? You want a bar construction?
What I mean is the following thing is, let me write this way. We have F.
What does it mean?
Yes, we have V. Well, these are details though.
Yeah.
But let me write something. Then if I have this condition, I can define some other Feynman category, where basically I keep track of the sequence of phis that I took. So let me call it B-oriented. And then so I have, sorry, this goes the wrong way around. So I have two inclusion maps, I and J, and the Feynman transform will be I upper star, J lower star of all. And this gives you actually, so this gives you, and maybe, sorry, O, and for you it's better to start with, or where O is in F op. So it's a co thing, and then I can do the co-bar construction, and I get a new thing. Okay? And I can give you many examples. So co-bar is one of these. So co-bar for operads. Co-operads. This lands in odd operads.
But then you seem to say that it works for everything, including props.
Including props.
So you have a bar construction for props.
I have some sort of bar construction for props.
Or
yes.
you have a co-bar for something that you call co-props.
Yes, I have a co-bar for something that I call
This makes sense, but the bar for props.
This is the co-bar for co-props. And the thing is that then the degree of horizontal is 0. It's weird. Then 2.
So it's, I mean, it will act in kind of category of corporates.
Yeah, it's actually, and then there's a DG, so there is some action. I can, as I said, I can give details. Let me just say 2 or 3 things, and then I can give details if not. So then there are universal things, and this I really want to say. This, if anything, I will say 2, and 3, there is a model category structure. And basically, this is by transfer. From C, and it has to be nice, and then one of the theorems, so there are several theorems about this, whatever, but one of the theorems says that this Feynman transform is called Feynman. And in the original Getz-Kapanov, you take O and you take O dual, which is a co-operand, and then you take this. And it's basically what you have to do is you have to add this twist, the determinant thing, and that if you do this
So
thing,
just
it's
one question,
something.
if you start from F to F with those tilde or something, if you do
Obvious.
this twice, do you get the same? Is it an involutive construction on Fs?
If you have duals, I mean, this is
Yes,
the thing.
if
If you have duals, then it's
that
involutive.
That for F there is like a dual F,
Yeah.
a double dual to.
Yes, you can
F
do
is
this.
like F.
Yeah,
Oh,
exactly. You can
sure.
do this. Yeah, but you need this sort of depends that you have duality on the
Yeah,
category
yeah, of
C.
course.
Then you can dualize and you get a co-op
Yes, yes,
thing,
yes, yes.
and that's what you used. But then then Bruno doesn't understand because he doesn't like to take duals. So I had this conversation with
I
him.
can understand duals. Just I know that the dual of an algebra of an operad.
Yeah. So the thing that's kind of fun. So I do want to say something about universal, and this is sort of related to the Venus conjecture and this considered Soilman operad and pre-Lie and so on. So I mean, one of the questions I always had is where do we get these things from? I mean, we know they exist. We know that they operate. You know, I proved some of the stuff that these things operate. But now I can actually say where they come from. So what you can do is we go to what we have to look at. We have to look at the free co-completion of this category F. Call this F hat. And then usually it's let's not be enriched. Then F hat. This is just species on this guy. Set, and this F goes to F hat by unit embedding. And you can do this in rich, but then it's complicated. But it's all kosher. You just have to read Kelly's book. Then I guess you have to restrict to accessible functors. It's a little tricky, but okay. So look at this. But then we have standard objects. So we can look at the following thing. I define the object circ to be equal to colon over V tensor and inclusion factor. Okay, this is just one object. And now I can look at tensors of these. So look at the category inside, so at the category symmetric. So this has day convolution. I can look at the symmetric monoidal category sitting inside. Actually, it also has a trivial center. Category spanned by spanned by tensors. Spanned by tensors. And there is a naive way to do it, which I actually want to do, but I think it's the same way that you would get with day convolution. So and it's morphism. In F hat. And so then the theorem is, this is again Feynman category. And now I can make a list, which is kind of nice. So, but maybe the easiest example, so the nicest example is if I start with the Feynman category for operads, what I actually get is the Feynman category for pre-Lie algebras.
For what?
Pre-Lie algebras. So if I had an operad, I had a Feynman category for it. And this construction tells me that if I start with this guy, I get this pre-V. And if I start with F,
Or you get associative algebra. If you
Sorry?
start from with operas, you get BV. No?
no, oh yeah, that's a B. Where would you get BV? If you start with F, NC, unmarked. So this is what is called G, right? So if I start from G, I get something that's bigger than BV because this is also not Lie, right? This contains Lie. So this is actually so I get something which contains BV.
It's a non-commutative version of BV.
Non-connected. And BV means that you have the BV equation. For that, you need a multiplication. The multiplication is the horizontal composition. So this is the theorem I wanted. Namely, if you look at these papers, then you see if you take the Feynman transform topologically, which of moduli spaces, which is the real blow-up of KSV blow-up, then if you look at the chains, they have this strange modular, this strange operad structure, and they have a BV thing. And the BV thing is so this has product which is disjoint union, and I always found that very strange in how this comes about. So you get this BV, and so for operads you get this, and if you do this as operads with multiplication, basically you get the Linus conjecture. So you get these exactly. So what are the morphisms? The morphisms are given exactly by these black and white trees. So these are morphisms. And if you do this with operads with A infinity multiplication, you get these considered standardized. And you have to be a little bit careful, but I was told I should go about 1 hour and 20 minutes. I can explain this is really nice. Maybe one thing I should say. So here there's something about signs hidden here. If I go to this guy, so I guess I want to realize this, but I think it hasn't permeated too much. It's if you do this, okay, then Dylan Thurston realized it.
He was the referee. This version.
Okay, so the point is that you have to you have to add signs. And the way you do that actually is you go to a twisted modular operad, which is called K modular operad. This is even true, so the general setup tells you that this is also true for operads, props, properads, and so on. In those cases, you can shift your way out of having these signs, okay? And that causes some confusion. So if you have to be careful in these statements. So to get the things you would expect, you just have to start with the odd things. So I was cheating here a bit. You have to take the KG to get BV. Otherwise, there are no signs. You have to have that if I have one generator and another generator, I interchange them, I get signs. And the same thing here to get. So here you do get pre-Lie, but if you want to get the graded version. So let's see. Then you get the. So this is a little bit confusing always, but this was sorted out in the paper with Ben Ward and Javier Zuniga. If you start from what, you get what. So if you start from an operad, then you actually don't get Lie, but you get odd Lie. If you start from an odd operad, you get Lie, and then you can shift yourself back. And this is why you get this. If you start with an odd operad with multiplication, you actually get Poisson. But if you start with an operad with multiplication, you get Gerstenhauer. So somehow it explains where these strange signs come from.
This is given particular case that if you start with a linear operad, you get a Lie algebra. If you start with prop, you get associative algebra.
Yeah, exactly.
Exactly.
And morphism from the Feynman transform to your guy is a solution to the master.
Exactly. So yeah, that was what we wrote in this paper. So the next statement here is you can do this Feynman transform. Then this thing is called Feynman. You can add. So there are two questions you can ask: what are morphisms of this Feynman transform? They're solutions of the correct master equation. And here in these guys, this is just the usual master equation. So this is just B plus 1/2 bracket, and here you would get B plus delta plus 1/2 bracket. And this delta is sort of this BV part, because the simple things, but it's exactly like pre-Lie. So pre-Lie is great. So because pre-Lie, so one thing that's strange, what happens is you start out with a Feynman category that is generated basically in degree 2, or namely just from 2 stars to 1 star. But then this is generated in all degrees. You have a generator sitting in every degree because you're taking these colimits. But it's kind of fun. So these pop out for free. And they basically live as on SN co-invariance. So in your paper with Manin, so Kapranov-Manin paper, you realize that the bracket actually lives on the co-invariance. And so it's kind of nice, then sometimes you can lift them. So you can lift them because you have an inclusion of Feynman categories from non-sigma guys to sigma guys. And so also in the paper with Ward and Zuniga, we found out something which is funny. So on cyclic operads, you have a bracket, you don't get pre-E, you only get a bracket. But this bracket, when you can actually lift it, but only to cyclic invariance. You can't lift it all the way, but to cyclic invariance. And the reason is because they're non-sigma cyclic operads. There is no, but those still have a CN action.
Yes.
And you can never get rid of the CN action. So if you do this construction, you see that you're always taking CN co-invariance. So you can pull it back, but you can only pull it back to CN co-invariance. So more or less everything, or anything you ever want to say about these operad things, it's just a con extension or a push forward or a pull back, and all life is natural.
Thank you. Do we have time? Yes, we have time for short questions maybe, and if you want to come back for more details for those who do not play soccer. Any short question? Since we asked all the questions already. So thank you.
Okay.